energy transport by heat and also by work. Okay, under energy transfer, so we have two categories in terms of energy transfer. First, energy transfer by heat, and the other one is energy transfer by work. Okay, so under the energy transfer by work, we have different kind of work transfer, such as mechanical work and also non-mechanical work. So under non-mechanical work, we have electrical works and also magnetic. So in this chapter, we will discuss only electrical work for the non-mechanical works. However, for mechanical works, so we have shaft work, spring work, moving boundary, where the moving boundary we will describe more in detail in specific subtopic. We have elastic solid work, stretching of liquid film work, and the body acceleration work. However, under this mechanical works, we only discuss the shaft work, the spring work, and also the moving boundary works. Okay, so last time when we discussed about the about the energy in chapter, is I'm not mistaken, in chapter number 1. Okay, for example, we have a system. Okay, the red dash line represent the boundary. So this is the pistons in the device, and we consider the system as the closed system. We already learned that the energy can cross the boundary for the closed system. This energy can cross boundary through the heat transfer or through the work transfer. Okay, so now we want to discuss about the energy transfer or energy cross the boundary through the heat transfer. So energy transfer by heat. So heat actually the form of energy that is transferred between two systems or a system and its surrounding by virtue of a temperature difference, which means the keywords for the heat transfer is the temperature difference. For example, at initial condition, we have a cold soda can at 5 degrees Celsius. Let's say the surrounding is at 25 degrees Celsius. Due to the temperature difference, the heat will receive by the soda can from the surrounding. Okay, so we have heat transfer from the surrounding to the cold soda can. And at the final state, so we'll have warm soda can at 25 degrees Celsius, which is equal to the temperature of the surrounding. Okay, which is equal to the surrounding temperature. And at this condition, we consider as the thermal equilibrium, because the temperature of the system is equal to the temperature of the surrounding. Okay, another example, for example, we have a hot coffee and the temperature is 60 degrees Celsius. We consider this as initial state, and the surrounding also at 25 degrees Celsius. Due to the temperature difference, so we will have heat transfer. So now for this case, heat will transfer from the hot coffee to the surrounding. The hot coffee will release heat to the surrounding. At the final state, the coffee temperature will be equal to the temperature of the surrounding, which is 25 degrees Celsius. And at this condition, we consider as the condition as, or the state as, the thermal equilibrium state. So in terms of heat transfer direction, in natural condition, the heat will transfer from high temperature medium to low temperature medium. And the system we consider without heat transfer if there is no temperature difference. The process where no temperature difference, or the process where no heat transfer, we call the adiabatic process. For example, we have a rigid tank, and the fluid inside the rigid tank is 25 degrees Celsius, and the temperature of the fluid inside the tank and inside the rigid tank is equal to the temperature of the surrounding. So for this condition, no heat transfer occur. Okay, so this case is considered as adiabatic process. Another example or another case is a rigid tank with what I call the temperature of the fluid or gas inside the rigid tank is 80 degrees Celsius, and surrounding the tank we put an insulator. An ideal insulator where we not allow any heat transfer in or any heat transfer out, and the surrounding temperature is 25 degrees Celsius. Due to the insulator, the perfect insulation surrounding the rigid tank, we consider that no heat transfer in and no heat transfer out. So for this case also, we consider the case or the process as the adiabatic process. Okay, so no heat transfer occur for this case. Okay, now we want to see what the difference between the thermal energy and also the heat. Okay, so we want to look what the difference between the thermal energy term and also the heat terms. So let's say we have piston cylinder device, so we have red dashed line represent the boundary. So inside the piston cylinder device we have water. In terms of substance, we have water, and we provide heat in order to increase the water temperature. Let's say the temperature increase to 100 degrees Celsius, and the water receive amount of energy around 10 kilojoule. So the energy that's stored in the water we consider as thermal energy. And let's say the surrounding temperature is 25 degrees Celsius. Due to the temperature difference, so we will have heat transfer from the hot water to the surrounding. Let's say we transfer heat, the system transfer heat to the surrounding around 10 kilojoule. So this 10 kilojoule of heat transfer we consider as energy in transition. So the heat actually is energy in transition if we compare to the thermal energy, and the heat associated with the process, not a state. And the heat we consider as the thermal energy that cross the boundary. So when the thermal energy cross the boundary, we consider that the energy as the heat. Okay, and then due to the heat transfer, the surrounding will receive energy also around 10 kilojoule. So the energy that received by the surrounding we consider as the thermal energy. So that's the difference between thermal energy and also heat. So in terms of heat transfer mechanism, there are three types of basic heat transfer mechanism. First, we have conduction, the heat transfer within the solid material, and the second one we have convection, the heat transfer between solid and fluid, and the last one we have radiation heat transfer, the heat transfer that relate with electromagnetic wave. In detail, you will learn what I call this type of mechanism, the heat transfer mechanism, in heat transfer subject. Okay, in terms of heat transfer symbol, we will use in thermodynamic the symbol Q symbol as the heat transfer symbol. So Q mean heat transfer, the unit will be kilojoule, and Q small letter represent the heat transfer per unit mass, and the unit will be kilojoule per kg, and Q dot represent the rate of heat transfer, the unit will be kilojoule per second or kilowatt. Okay, now about heat transfer equation. Q capital letter equal to mass multiplied by heat transfer per unit mass, Q small letter. And in terms of specific formula for the heat transfer, if the rate of heat transfer is not constant, where it depends on the time, so Q capital letter equal to integration of Q dot dt. T2 is the time for final state, T1 is time for the initial state. So if the heat transfer process is constant in terms of value, so Q is equal to Q dot multiplied by what I call temperature change, delta T. Okay, so in terms of direction, or the symbol that to describe the direction of heat transfer, so heat transfer in or heat transfer to the system direction will be positive value. Okay, we can just write down Q equal to positive value, or we can just round Q in equal to certain value. Okay, so that the symbol that we use for for heat transfer in or heat transfer to the system. However, for the heat transfer out or heat transfer from the system direction, the Q value will be negative, or we can use symbol Q out. Okay, for example, so we have a rigid tank. Inside the rigid tank we have the hot fluid or hot gas. So we have heat transfer in and heat transfer out. For example, we have heat transfer out. The amount of heat transfer is 4 kilojoule. Okay, heat transfer out from the system. So we can write down in terms of heat transfer value, Q out equal to 4 kilojoule, or Q equal to negative 4 kilojoule. So for heat transfer into the system, let's say the value is 3 kilojoule, so we can write down the heat transfer process value or symbol equal to Q in equal to 3 kilojoule, or we just type in Q equal to positive 3 kilojoule in thermodynamic. If the symbol for heat transfer is positive, so we understand that the heat transfer into the system. If the heat transfer value is negative, so the heat transfer process refer to the heat transfer out of the system or heat transfer from the system. So the value will be negative. So let's say we're not sure about this about the sign of the heat transfer or the direction of the heat transfer. So first, in your analysis, you just put your assumption. For example, the heat transfer is Q out. When the value of the actual value that you obtain for Q out is negative, that means your assumption is correct. But if the value of Q out equal to positive, so that means your first assumption is wrong. The actual direction is for the heat transfer is Q in, because if the value is positive, so that's how you determine the direction of heat transfer. Okay, now we want to discuss about the energy transfer by work. Okay, as I mentioned before, for a closed system, the closed system will allow the energy transfer. Okay, when energy cross the boundary, so energy are allowed to cross the boundary for a closed system. So previous slide we already discussed about the energy that cross the boundary through the heat transfer. So now we want to discuss about the energy that cross the boundary through the work transfer. Okay, energy transfer by work. So work in terms of definition is the energy transfer associated with a force acting through a distance. Okay, for example, we have a piston cylinder device as initial condition where the temperature of the substance inside the cylinder is 25 degrees Celsius. So we provide heat. So due to the heat addition to the process, we have final temperature of the substance at what I call the 100 degrees Celsius, where the substance inside the cylinder expand due to the heat addition process. So we have a moving piston throughout the process and produce work. Okay, so now we have energy transfer process by work. Another example is a system of a rigid tank with a rotating shaft. Okay, so the energy transfer for this system also energy transfer through the work. Okay, or energy transfer by work. Okay, another example is the electron work. So for example, for the last example, we have the rigid tank with the electric heater. So inside the wire of electric heater, we have the what I call the movement of the electron inside the wire. So the electron doing work to the what I call to the system. Okay, so for the last schematic diagram we consider as electron work. Okay, what the difference between energy and also work? Okay, so we have cylinder piston device. So we have heat source due to the expansion of the substance inside the cylinder. So the substance expand, the piston will move upward and produce work. Okay, so this work is considered as energy in transition, and the work is associated with a process, not a state, and the work considered as energy that cross the boundary. Okay, so the description of the work is quite similar with the description of the heat when we discuss about the thermal energy versus the heat. Okay, in terms of symbol, work symbol, so we will use capital letter W. Unit will be kilojoule. Okay, represent the work, and the small letter W we refer as specific work or work per unit mass. The unit will be kilojoule per kg. And in terms of rate, so we have W dot, capital letter W dot, which is rate of work or power. The unit will be kilojoule per second or kilowatt. Okay, the work equation, so we have what I call the work in kilojoule equal to mass multiplied by specific work or multiplied by the work per unit mass, small letter W. And in terms of what I call integration equation, so we have W work equal to integration of rate of work W dot with the what I call the time dt. Okay, so integration of what I call rate of work with dt, with the time. So this is the equation when the rate of work is not constant. If rate of work constant, so we can use this formula where work equal to rate of work multiplied by what I call the time change. Okay, work done by a system in terms of direction, work out. So the symbol that we use for W out is positive value. So we can describe the work done by a system with W equal to the positive value, or W we just write the subscript out at the symbol of W. So we just put W out to represent the direction of work done by a system. And we have work done on a system direction, which is referred to the work in. So the value of W for the work done on a system is equal to negative value, or we can use the symbol of W in. Okay, form of work, we have numbers of form of work under mechanical works. So we have shaft work, spring work, moving boundary work, elastic solid, stretching of the liquid film, and also body acceleration works. However, we only discuss in this chapter shaft work, spring work, and also moving boundary work. So under non-mechanical work, we have electrical work and also magnetic work. So under non-mechanical work, we only discuss the electrical work. Okay, for example, in terms of direction. Okay, so what we call, we have here in the schematic diagram represent the work in, also work out. For work out from the system, we can write down W out equal to 4 kilojoule or W equal to positive 4 kilojoule. Okay, so if the work done on a system, which is referred to the work in, so we can just type in W in equal to 3 kilojoule or W equal to negative 3 kilojoule. Okay, so this is the what I call the explanation about the energy transfer by work.